All right, welcome to problem 3.26 of David Griffiths Electrodynamics. My name is Brandon Beresford, and yeah, I solve physics problems on YouTube because I like to do it for fun. So, without further ado, it's been a while since I posted a video. I've been gone for some time just because of, a lot of just life stuff going on, to be honest. I'm getting married next weekend. So yeah, I'm just a lot of stuff going on. So anyways, let's kind of jump into the problem and see what we're dealing with here. So it says that we have some surface here, a cylindrical surface, maybe like a wire or something, and like a copper wire, and we have some charge density psi, which is a function of phi, which is equal to a sine of 5 phi. And it's glued over the surface. And this is like an infinite cylinder. It has a radius of capital R. And we want to find the potential, the electric potential, inside and outside of the cylinder. All right. So let's kind of jump into here. So it says that we need to use our result from problem 3.24. So I've gone ahead and written the problem result from 3.24, which is essentially solving Laplace's equation in cylindrical coordinates, where there's no z dependence. So of course, cylindrical coordinates, you have z, you have s, which is the radial coordinate, and you have phi. But here we solved it assuming that it was uniform or symmetric about z. And so our solution to Laplace's equation only depends on s and phi. And this is kind of what we had. We have a naught plus b naught natural log of s plus the summation from 1 to infinity. We have s to the power k times a sub k cosine k phi plus b sub k sine of k phi. Then we have another term plus s to the minus k. And remember, this is all in the summation. C sub k cosine k phi plus d sub k sine of k phi, where a, b, c, and d are just summation coefficients, essentially. So to solve this problem, it's essentially solving a boundary condition problem. We have to use our boundary conditions to sort of narrow down this general solution to a more particular solution. And part of that is given that we know what the charge density is on the surface. So let's consider the potential inside of the cylinder. So inside of the cylinder, we have the origin. So s and phi could be 0. Really, in this case, s being 0 means that when we take this term, which is in the second half of our general solution, well, if s is 0 here, then this blows up to infinity. So we can't divide by 0 here. So what this is telling us is that inside of the cylinder, this general solution, this second term in the summation, doesn't make any physical sense. It doesn't. We can't have this term in our solution because it blows up. So physically, that part cannot be in our solution. Now, what else can't be in our solution? This term is fine. There's nothing stopping s being any value inside of the cylinder, s to the power of k. That's fine. But the natural log of s, that's fine as long as s is not 0. But since s can be 0 inside of here, then this is going to blow up to infinity, which means this natural log term also can't be in our solution. So I've gone ahead and written up here that inside of the cylinder, the potential is a naught, which is just some arbitrary constant, plus the summation from k equals 1 to infinity of s to the power k times this first term, ak cosine k phi, bk sine k phi. And then we're going to do the same sort of analysis for points outside of our cylinder. So anywhere outside of our cylinder, how is our potential function here limited? Well, 1 divided by s to like if s is very large, like infinity, right? We go out to infinity. Well, 1 divided by infinity is not a problem. It's just going to be a very small number. But s to the power k here on this term, that means infinity to the power something. That's just going to blow up to infinity forever. Like it's just going to get larger and larger and blow up to infinity. So this doesn't really make any physical sense for our solution outside of the cylinder. So we're going to drop off this term, as well as the natural log of s also blows up to infinity. If you put an infinity into a natural log of s, we just get infinity. So we're also going to drop off this natural log term of s from our general solution. And so those are part of our boundary conditions here. And so I'm going to write out the potential outside as a function of s and phi is a naught. We still have that, which this a naught and this a naught, you know, they can be the same. It doesn't really matter. It's just an arbitrary constant. But plus this summation, and now we're going to have this bottom term here, this second term here, 1 over s to the k times c sub k cosine k phi plus d sub k sine k phi. So we've narrowed down our general solution into two slightly more compact, getting closer to the particular solutions, but each one is for the inside and the outside of the cylinder. So we're kind of narrowing it down, but we're not quite there yet because we have these coefficients a, b, c, and d that are part of the summation that we don't know what they are. Okay, so what else could we do here? Well, again, the hard part of these problems is coming up with the boundary conditions and using those boundary conditions to sort of narrow down your general solutions into more particular solutions. So a boundary condition that on the potential, we know that from earlier in Griffiths, there's a whole chapter in section chapter 2 on boundary conditions, and it talks about how, you know, there's a discontinuity in the electric field across a boundary, across the surface charge, across a boundary. And you ended up writing that in terms of the potential because remember, you know, the electric field is the negative gradient of the potential, so you can rewrite that boundary condition for the electric field in terms of the potential. And you can write it out as the difference in the potential and the difference in the rate of change of the potential. Here we're kind of just expressing the gradient with a single derivative here with respect to the normal vector. So normal to the surface is equal to minus sigma divided by epsilon naught. Really, this is epsilon naught, where sigma is the charge density. So we can express our boundary condition from chapter 2 in terms of potential like this. Well, we know what the charge density is, right? We're given that. We have expressions for the potential outside and potential inside, right? There's a discontinuity in the electric field here, or a discontinuity in the rate of the change of the potential across the boundary, which is equal to this. So let's go ahead and do these derivatives. So we're going to, the normal component here, the normal is going to be x, right? Like the coordinate normal to the surface here is s. So we're going to take the derivative of both the out and the in potential here with respect to s. And then because we're interested in what these are at the boundary, we're going to evaluate the potential, these derivatives at the boundary. So when s is equal to the radius at r. So if we do this derivative, we get minus k s to the minus k minus 1. So we're taking derivative of this. So if you take s to the minus k, take the derivative of that, you get minus k, bring it down, s to the minus k minus 1. And then this term is constant. And we drop the a naught because that's constant with respect to s. So that's our derivative. We plug in r. We just get k divided by r to the k plus 1. And then we have this term here still. So that's just plugging in r equal to k here and kind of just flipping things around. All right, and then taking the derivative of this term here, we just get k r to the k minus 1. I just went ahead and plugged in r for s. So that's just taking the, doing the power rule for derivatives here. That's all we're doing is the power rule for derivatives. And then the other terms are constant with respect to s, so they just get left alone. All right, so we have those two derivatives. Now, we're going to come back over here. So we have this is the expression we're trying to evaluate here. So we're going to plug in these derivatives we just found and plug in our charge density function. So our charge density function was a sine of phi phi, where a is just some arbitrary constant that we know, given the problem. So a sine of phi phi is equal to, and I'm multiplied the epsilon naught and the minus sign over. So minus epsilon naught, and then plugging these in, you get the summation from k equals 1 to infinity. And then if you plug in this derivative, it was minus k divided by r to the k plus 1 times c sub k cosine k phi plus d sub k sin k phi. And then we have a minus the other derivative, so minus k r to the k minus 1, and then times a sub k cosine k phi plus b sub k sin k phi. So really just take your time. If that didn't make sense to you, just go take your time real quick and plug those in, and that's what you get. And then you can cancel these minus signs, right? Like the minus signs can cancel away. So we have positive now. And so what does this tell us, right? Right away. So this has to be equal to this. How do we get that to happen? Well, there's a sign over here. There's sines and cosines over here. So obviously there's no cosines on the left side here. So all cosine terms need to drop. That means c sub k and a sub k need to be 0. So what this is telling us is that our coefficients a sub k and c sub k is 0 for all k. No matter what k we're on, those terms have to drop. Okay, so that's good. We've knocked out half of the coefficients, so we don't even need to find those. Now, what about we're left with b sub k and d sub k? What do we do there? Well, we can see that we only have one sine term, so we know our summation should probably go away because we're not summing multiple sine terms here. We just have a single sine term, and our k value here is 5. So that tells us that the only term in our summation is when k is equal to 5. All right, so that tells us that both b and d are 0 except when k is 5. So we can drop the summation and only write the terms out with k equal to 5. So doing that, we have a sine of phi phi is equal to epsilon naught, right? We drop the minus sign, it's all canceled. And then plugging in for k, we plug in 5. So we have 5 divided by r to the 6th power, d5, right? So d sub 5 is just the fifth element coefficient in that summation. Everything else was 0. Times sine of phi phi plus 5 r to the 4th, plugging in 5, times b sub 5 sine of k phi, or sine of phi phi. So we just plugged in 5 for k and dropped everything. So we dropped a and c and just plugged everything in. And we get this expression. All right, we're getting closer. We need to figure out what is d sub 5 and b sub 5 though. What are those specific coefficients to make all this equal to this? All right, so just doing some more factoring. A sine of phi phi, let's try to make the form of this match this. So factor out sine of phi phi, and we get epsilon naught, all of this, right? D sub 5, b sub 5 times sine phi phi. So that tells us that this whole term is a. That is what a is. Right? So a is equal to epsilon naught 5 divided by r to the 6th, d sub 5, plus 5r to the 4th, b sub 5. Okay, I mean that's useful, but we have one equation and two unknowns. So we can't quite solve this yet, right? If we had two equations with d sub 5, like b sub 5, we could go ahead and solve this. So we need another boundary condition. Okay, so we use the fact that the electric field is discontinuous. Well, what about the potential? The potential is continuous across the boundary. We know that from chapter 2. So let's use that. So the fact that the potential inside and the potential outside right at the boundary, so we plug in R for S, so right at the boundary of the surface, it has to be continuous. That means that they both have to be equal. There's no difference in the potential across the boundary. That's what it means to be continuous. Okay, so let's use this condition. I dropped that. So we're going to set Vn, and we're going to write Vn and Vl, but these have now been narrowed down, right? Because now we know we don't have a summation. We only have the fifth term in our summation. So we have Vn is equal to A naught plus R to the fifth b sub 5 sine of phi, right? And if you don't understand how we got that, we had this. So we have A naught, we drop the sum, and then now we have R to the fifth. We don't have this term, b to the fifth sine of phi. So we're just plugging in what we know into our previous forms we had. Just keep on narrowing down our solution into something more particular. And then the out potential is A naught plus d sub 5 divided by R to the fifth, right? Plugging in R for S times sine of phi. These need to be equal at the boundary. So we're going to set those equal to each other. So here, we're going to set those equal to each other. And then, because A and A naught, those are just constants, right? Our solution, though, hasn't told us or put any constraints on those constants. No matter what A naught is, we're going to have a solution. So let's just make it 0, right? Just for the sake of making the math, the algebra, a little bit easier, let's just pick a solution where A naught is 0. So we're going to drop the A naught terms off, right? Cancel those off. And rewrite it. So we have R to the fifth, b to the 5 equals d to the fifth over R to the 5. And the sine of phi cancel. And so we solve for d sub 5 in terms of b sub 5. So d sub 5 is R to the 10th times b sub 5. Right? So what does that tell us? What can we do with this? Well, now, okay, we had an equation, so this is our second equation. This was our first equation. This is our second equation. We solve for this variable in terms of this variable. So let's plug in this for d sub 5 here. And then we can solve for b sub 5 in terms of d sub 5 and A. So that's what we're going to do. So we have A equal to epsilon naught times 5 over R to the 6. And then we're plugging in R to the 10th b sub 5, right? Plus 5R to the 4th b sub 5. And then just rearranging things, factoring out the b sub 5, and canceling out factors of R here. So this becomes R to the 4th. So we have 2R to the 4th here. Essentially what we get is that A is equal to 10 R to the 4th b sub 5 epsilon naught. And we just rearrange, right? So we're solving for b sub 5, so b sub 5 equals A divided by 10 R to the 4th epsilon naught. Right, 10 because this is 2R to the 4th, so 2 times 5 is 10, epsilon naught b sub 5. And then, now that we know b sub 5 in terms of A and R, which are values that we know or are given, right, A is just an arbitrary constant that was in our problem. It was in the charge density. It just Griffiths says it's an arbitrary constant. So no matter what A is, this will all work. Then we can figure out what d sub 5 should be. So plugging in this into d sub 5, we get d sub 5 is A R to the 6th divided by 10 epsilon naught. So there we go. We have our two coefficients. These are our equations. What we didn't know was b sub 5 or d sub 5. Now we have them. We have b sub 5 and d sub 5 in terms of things that we know. So all we got to do is plug those in. So the potential inside, if you plug all this in, is S. So the potential with respect to S and phi is A divided by 10 epsilon naught r to the fourth times S to the fifth, right? Because K is 5 here, times sine of phi. And the potential outside is A r to the sixth divided by 10 epsilon naught times 1 over S to the fifth times sine of phi. So literally, if you just plug in like 5 and our coefficients into those equations, just do the algebra, that's what you get. Then just rewriting this in a little bit more compact form, there's a lot of shared terms here, so we can write this as A sine of phi, right, divided by 10 epsilon naught. Those are the common terms. And then depending if we're talking about inside or outside, if we're talking about inside, then we have S divided by r to the fourth, or S to the fifth times divided by r to the fourth. If we're talking about outside the cylinder, then we have r to the sixth divided by S to the fifth. So this is just a slightly more compact way to write the solution. But really this also works, right? Like this is the potential inside and outside. And that's it. So that was a little bit of a long problem. But I hope I sort of explained how my thought process and how I went about solving this. If you guys have any questions about what I did here, if you see a mistake, please point that out in the comments. I'll try to address it. We can pin a comment if there really is a mistake so that other people who watch can see that mistake, like a minus sign or something, but I'm pretty certain that this is correct. But yeah, if you guys have any questions, drop them in the comments below. Other than that, I'll see you guys on the next video. So, bye.